Hello everyone, I'm Jiangwei Liu from National Institute for Materials Science, NIMS, Japan. The title of my presentation is Deposition and Mechanism Study for Super High Dielectric Constant, Aluminum Oxide, Titanium Oxide, Nanolaminates. This work is collaborated with Panasonic Hose Corporation, Japan. Firstly, I will show my personal experience. I graduated from the University of Tokyo in 2012. Then I joined NIMS to be a postdoctoral researcher. From 2014, I was a SUS fellow. From 2016, I became a permanent independent scientist. This is a permanent position and also supported by the GSPS Leader Program. From 2018 to 2023, I was a senior researcher at NIMS, and from this year, I became a principal researcher. Next, I will introduce our institute, NIMS. NIMS is one of 3 special national research and development agencies in Japan. We not only publish world-class research results, but also give suggestions about national research strategy. Other 2 special national research and development agencies are AIST and RIKEN. NIMS is located at Tsukuba Science City. We are close to Tokyo. It takes around 1 hour from NIMS Institute to the Tokyo station. The environment at Tsukuba Science City is very beautiful. There are many universities and institutes. This is the outline of my presentation. First, I will show the background, then experimental conditions, effects on aluminum oxide, titanium oxide nanolaminates, ATO nanolaminates. Third one is the mechanism discussion for the formation of the ATO nanolaminates, and the fourth is the conclusion. First, for the background. The first question about why ATO nanolaminates and the GIT insulator. This figure shows the polarization and the whole consideration and the function of electrical field. The high dielectric constant materials can provide the large charge response and small bias voltage. This equation shows the relationship between output current of the MOSFETs with the capacitance and the high dielectric constant. The higher dielectric content materials are important to enhance the output current of the MOSFET and the same gate voltage. Around 20 years ago, Professor Achiro Orlando's group fabricated the super high dielectric content ATU nanolaminates with a dielectric content as large as 1,000. Therefore, we can choose this material for the fabrication of electronic devices. We have fabricated the ATO nanolaminates, aluminum oxide buffer layer, diamond MOS capacitors, and MOSFET. The deposition temperature for all of oxide insulators are 250 degrees C, with the sublayer thickness of 0.35–0.7 nanometer. The total thickness for the oxide insulators are 57.5 nanometer. The capacitance maximum for the nanolaminate is 1.06 microfarad per square centimeter, which is larger than the titanium oxide, aluminum oxide by layer of 0.83 microfarad per square centimeter. The dielectric content for the nanolaminate and the total insulator are also much larger than the bilayer oxide insulator or the single titanium oxides. We also succeeded for the fabrication of ATO nanolaminates aluminum oxide buffer layer diamond MOSFETs. With the increase of gate length for the MOSFETs, the drain source current maximum decreased greatly. However, all of the MOSFETs show very good operations. Therefore, we have succeeded for the fabrication of ATO nanolaminates-based electronic devices. However, the studies for the ATO nanolaminates are still not enough. For example, the effects of experimental conditions and the mechanism for the super high dielectric constant are still under discussion stage. Both of them are the objectives of this study. Next, I will show the experimental part. This is the fabrication process for the metal ATO nanolaminates metal capacitors. The first step is the bottom titanium-platinum electrode formation using evaporator technique. Then the ATO nanolaminates were formed using the ALD technique with the precursors of TMA, TDMAT, and water vapor. Then the surface titanium gold electrode were formed on the nanolaminates. The last is the nanolaminates were etched using CCPRIE system to open the windows for the bottom titanium-platinum electrodes. We try to change the experimental conditions to confirm their effect for the capacitor. We change the deposition temperature for the ATO nanolaminates from 120 degrees C to 250 degrees C. We also change the ATO sublayer thickness from 0.34, 0.73 to 0.77, 0.19 nanometer. We also changed the ATO nanolaminate total thickness from around 50 to 200 nanometer, and also changed the number of ATO interfaces from 25 to 194. Next, I will show the experimental result. This figure shows the schematic diagram for the capacitor. We measure the surface metal and the bottom metal for the electrical properties. Based on the STEM and the EDX mapping, we can get a conclusion that the ATO nanolaminate has been fabricated on the silicon substrate successfully. This figure shows the Raman spectra for the single ALD aluminum layer and the single titanium oxide layer. We also changed the sublayer thickness for the ATO nanolaminate to measure the Raman spectra. The intensity ratio between two peaks at the position of 1534.6 and 618.9 per centimeter are 0.93, 1.09, and 1.46 respectively. With the increase of aluminum oxide content for each sublayer, the shape of the Raman spectra is close to that of the single aluminum oxide layer. Next, I will show the deposition temperature effect for the electrical properties of the capacitors. The deposition temperature for the ATO nanolaminate was changed from 150 degrees C to 250 degrees C with a similar ATO thickness and a similar sublayer thickness. With the increase of deposition temperature, the linkage current density also increased greatly. The capacitance maximum for the 250 degrees C deposited nanolaminates are larger than those deposited at 150 degrees C and 200 degrees C. With the voltage change from 0 to 5 volts or 0 to minus 5 volts, the capacitance maximum decreased greatly. The loss tangent for the 150 degrees C deposited nanolaminate-based capacitor are much lower than those deposited at 200 degrees C and 250 degrees C. Next is the total thickness effect on the electrical properties of the capacitor. The deposition temperature was fixed at 200 degrees C. The total thickness was changed from 50 nanometer to 200 nanometer. And the sublayer thickness was changed from 0.5 nanometer to 2 nanometer respectively. For the case of sublayer thickness of 0.5 nanometer, the increasing of total thickness cannot affect the linkage current and the capacitance maximum. However, for the case of 2 nanometer sublayer thickness, the linkage current decreased greatly, and the capacitance also much lower than other ones. With the increasing of the voltage, the capacitance for the 0.5 sublayer thickness decreased greatly. However, for the case of 2 nanometer, it's very stable, and the loss tangent of 8 are also much smaller than other ones. Next is the ATO sublayer thickness effect on electrical properties of the capacitor. The deposition temperature was fixed at 200 degrees C, and the ATO nanolaminate thickness are also very similar. The ATO sublayer thickness changing from 0.34, 0.73 to 0.77, 0.19. With the increasing of aluminum content for sublayer, the linkage current decreases greatly. The capacitance maximum of 8 is also much lower than other ones, and the capacitance very stable with the change of voltage. The loss tangent of 8 is also much smaller than other ones. This is a summary of experimental conditions effect on the electrical properties of the MIM capacitors. The maximum capacitance is as large as 3.64 microfarad per square centimeter, and the K value is as large as 443.5. We can give a conclusion that a lower deposition temperature, thinner ATO nanolaminate, and lower titanium oxide content in each ATO sublayer can lead to a lower linkage current and smaller loss tangent at 1 kHz for the capacitors. In contrast, a higher deposition temperature, larger number of ATO interfaces, and higher titanium oxide content in each ATO sublayer are important for obtaining higher K value for the ATO nanolaminates. This slide summarizes the dielectric content of the ATO nanolaminate with the change of experimental conditions. When the deposition temperature increasing from 150 to 250 degrees C, the dielectric content of the ATO nanolaminate changing from around 50 to 175. With the increasing of number of interfaces for the ATO sublayer, the dielectric content increasing from lower than 10 to more than 400. On the other hand, with the increasing of titanium oxide content from 0.2 to 0.7, the dielectric content also increased greatly to 400. Based on the LV characteristic, we also can receive the resistance for the ATO nanolaminates. When the ATO nanolaminates are semiconductors, the dielectric content of them are higher than 100. In other words, they are higher than those of the single titanium oxides. However, when the ATO nanolaminates is insulator, the dielectric content of 8 is lower than 100. Last, I want to discuss the mechanism for the super high dielectric content of the ATO nanolaminate. As mentioned above, when the ATO nanolaminate is semiconductor, the dielectric content is very large than 100. Actually, when the nanolaminate is semiconductor, we cannot consider it is a MIM capacitor. It is just double Schottky electrode contact mode for the devices. When the voltage is positive, with the increase of this voltage, actually the deposition layer width on the bottom area is very large. In this case, the K value for the ATO nanolaminate increased. On the other hand, when the voltage is minus, the deposition layer width on the surface electrode increased greatly. The K value for the ATO nanolaminate also increased. For both cases, A and C, actually the deposition layer widths of them are larger than that with the voltage of 0. In this case, the capacitance for the A and C are much larger than the B. In other words, with the increasing of voltage from 0 to 5 or from 0 to minus 5 volts, the capacitance decreased greatly. Therefore, this is in good agreement with our experimental measurement result. Therefore, we believe that the super high dielectric content of the ATO nanolaminate is attributed to the double Schottky electron road contact mode. In conclusion, in this study, effects of ATO nanolaminate deposition conditions on electrical properties of the capacitors were investigated. The higher deposition temperature, larger ATO interface number, and higher titanium oxide content in each ATO sublayer were important to enhance the K value for the ATO nanolaminates. The higher linkage current or lower resistance for the capacitance were relative to the higher K values for the ATO nanolaminates. More dramatic were variation for the CV curves and larger tangent dirt values. With the increase of resistance for the capacitors, the ATO nanolaminates varied from semiconductors to insulators. The double Schottky electrode contact mode was employed to employ the variation of capacitance with the increment of the absolute voltage. The super high K value for the semiconducting ATO nanolaminate were possibly attributed to the accumulation of depletion charge caused by the Schottky electrode contacts. Thank you very much for your attention.